motion question and example. So the first part of the question is setting up a bit of a parameter for us. A string 50 centimetres long will break if a mass exceeding 40 kilograms is hung on it. So that tells us the maximum force the string can take. So force equals mass times acceleration. So we have this string, we have a 40 kilogram mass on it, and the acceleration will be acceleration due to gravity g. So in other words, the maximum force for this string is going to be the 40 kilograms multiplied by acceleration due to gravity. So maximum force is 40g. So a mass of 2 kilograms is attached to one end of the string and the string is revolved in a horizontal circle. So now what we're doing is we're attaching a 2 kilogram mass and we're going to rotate it around in a circle like that. Okay, there's what's happening now. And it says find the greatest angular velocity without the string breaking. So we know we can only get up to this force. And because we have now circular motion, it's horizontal circular motion, we're going to have to look for an equation. And we know that a force, which equals mass times acceleration. We know our maximum force is 40g. And mass times acceleration for circular motion, when we're looking at the greatest angular velocity, we'll use the mr omega squared. So we'll use mr omega squared, and we'll have to say that that can't be any bigger than 40g. If we get to 40g, string will break. And so then it's just a matter of saying, well, our mass is going to be 40. No, sorry, our mass is now 2. Our radius, it was a 50 centimetre string, put that in metres, times 0.5, times omega squared has to be less than or equal to 40g. We'll just say, well, that's 1, so that's just omega squared, less than or equal to 40g. So omega has to be less than or equal to the square root of 40g. And that's the maximum angular velocity before that string will break. Not so much another example, but just to set you up for some of the questions from the textbook. The textbook likes to consider questions where we have a particle moving on a table in horizontal circular motion, and it's connected to a string, and in the center of the motion is a hole in the table, and so the string comes down below the table like this. So we have a mass up here, and we have another mass here. Now, what it likes to do is it talks about the tension in the string. And so it says there must be tension in this string. And so the tension is simply the force on the string. And so the force on the string for a particle in horizontal circular motion, that tension there is going to be equal to, say, mv squared on r, or mr omega squared, depending on which format you want. The tension down here with this other mass, assuming the mass is stationary, it's not swinging around wildly, then the force acting here is mg. So the tension on that force, on that part of the string is mg. Now if these are connected, going through a smooth hole, so we're discounting friction up here, if it's a continuous string, then these two tensions must be equal to each other. So we get the case of mg equals mv squared on r, say, if we're working in v, tangential velocity. So some of the questions in the textbook use this concept. Sometimes the masses are equal, so that's easy. You can just cross the mass out and go ahead and do what you need to do. Other times the masses will be different. You'll have to consider how you're going to do that. But that's one of the concepts that the textbook will explore. Sticking to the theme of textbook questions, another style of questions in your textbook is the idea that we have center, we have a string, we have two masses on the string, so we have this mass and we have this mass out here. The string stays straight, both the masses moving in horizontal circular motion, and so we start to explore the forces that are acting on this. Now, obviously the force acting in here is mr omega squared, little mr omega squared, in this one here. That's the force here, this particle is exerting. This particle here is similarly experiencing another force, and it will be the tension at this point here, this tension, I'll call it tension 2, I'll tell you why in a minute. So this particle is experiencing tension 2 back into the centre here, and tension 2 is going to be equal to mr omega squared, where r is the radius from the centre to the outside edge, little r would be the radius inside. And the question will start to talk about the tension on the string in here. So this T1 in here, what tension is being exerted on the string here. And this T1 is going to be acted on as well by T2. So T2 will be pulling away on this weight. The tension 2 will be pulling away on that. It'll have T1 pulling on the centre. And so this resultant force to keep this particle in uniform circular motion, their force must be the combination of T1 and T2. But T2 is actually pulling away from it, so it'll be T1 minus T2. Force equals T1 minus T2. So you get this mr omega squared is going to equal T1 minus mr omega squared. So have a think about that. And as I said, that definitely will help you with question 7. Well, I hope it helps you with question 7.